Well, I think it is time to start the lecture, and it's a great pleasure for me to welcome Majid Hassanizadeh. He is a professor in Utrecht University, as you can see here, in the Faculty of Geosciences, very geological. Now, it is a long time ago, of course, that I have been working there. I actually graduated in Utrecht more than 50 years ago, mind you. Anyway, but as long as you do science, and he is a witness to that, you stay young and healthy. So that's what I'm trying to do. Now, it's a great pleasure. It's not the first time I met him, of course. It's a long ago. He was interested in work that I had been doing, and he proceeded to go to Glasgow, and there he met Ian Murdoch, and he wrote on the basis of articles, and you have seen the articles, 3 of which I wrote together with Ian, and then Majid wrote a wonderful article together with Ian about how to go from a description on the molecular level in a porous medium to a description on the macro level. And of course that's a subject that is of great interest to us. And aside from that, I want to mention that he is a member of the advisory scientific board of PoreLab. Aside also, I mean, he is one of the founding members, if I understand it correctly, of Interpor. And you know Interpor, at least many of you have been to Valencia this year to the meeting. And furthermore, I mean, and that is of course a very important accomplishment he has been doing, and is considered to be a great master in the application of non-equilibrium thermodynamics to porous media. And that is a subject actually that we are here also extremely interested in. So I look forward to see this week and to next week to be able to discuss that subject with him and to learn something. And maybe he could even learn something from us. Definitely. That would be very wonderful. Anyway, so let me not stop you from lecturing. Please, Majid.
Thank you very much. Thank you for the nice introduction. It's great to be here. I have known most of you, as Dick said, from a long time ago. I've known Alex from, actually initially from his papers. I learned about pore scale modeling and pore network modeling and other numerical approaches. And I must say I've never given a short course to so many senior students. Well, actually senior scientists. So it's a little bit uneasy to do that. I hope I won't make any mistakes, but that's okay. We're all human beings. I make mistakes. Well, sometimes I make intentional mistakes, see whether you catch it or not, you know, so we'll see that. And I must say also the first part of the lectures, from the molecular picture to the microscopic, it's particularly uneasy for me to give a lecture in front of Dick. He's been a pioneer in developing these kinds of this approach. But anyway, I give a layman's translation of his work. I hope I'll do fine, other you should interrupt. Okay, so I have indeed sent to you via Marie-Laure a list of reading material for the first part of the lecture, which is from molecular going to the microscale. That's my own notes, and as I mentioned, there are papers of Dick and Ian Murdoch. Actually, there were more papers. There's also one from 1994 that I also used later, and then my own work with the Murdoch for multiphase media. Yeah, so the first part of this lecture actually is about this. we are all so comfortable we're talking about pressure and temperature as if they really exist. Pressure doesn't exist. Temperature doesn't exist. These are constructs. We make them up. Concept we make up in order to be able to describe processes. For me, pressure is not, but the same goes for viscous stress and diffusion and diffusivity, internal energy, heat flux, you name it. None of them really exist. Then you can get philosophicals. Okay, what does exist? Is mass exist too, or do we exist? There are philosophers say no, we are just reflections of what is going in our mind. I don't know, but in terms of real entities, I would say they all have at least partially the origins in the molecular description and the movement of the molecules and the way we perceive or we observe or we see the movement of the molecules, which actually we don't. We don't see the movement of the molecules, and therefore we translate that into these concepts. And that's what this part of this lecture is going to be about. This is what I call averaging thermodynamic approach to develop basic equations of flow and transport in any system for any kind of processes. So when I say any system, that means if I'm just interested in a fluid or a liquid or a solid or a medium that's filled by solid and a liquid or multiphase systems, I'm interested in flow, solute transport, electromagnetic, whatever process. In principle, you should be able to use this approach in a systematic fashion to start from some basic fundamentals that there is no discussion about it. As I said, pressure, yeah, you can discuss, but there are some starting point that say, okay, we can all agree on that. And then from that build up and develop not the equations that you don't know. In the past, I have seen averaging that has been done in porous media especially, where they know what they want to get, then they make reasonable assumptions, convenient assumptions to get it. Now, okay, I would say it would be very useful if you get what you don't know you should get from the averaging. And that's, I think, has happened here with this approach, and I hope I will show you some of them. Now let me ask a question. Neville Stokes equation. Is that a law? Is that an approximation? What is it? Someone please can give an answer. What do you think? Yes, sorry that I point to you. One of you. Yeah.
Well, it's quite general, so in that sense it's a law. It sort of covers a lot of different things, but
okay.
It is an approximation of several things, so I would say no, it's just an equation that describes something.
So actually it's not a law,
no.
Because an approximation is okay. No. Yeah, and others agree with that? Any addition to that?
I would call it a law, because
Okay.
at that level,
Yeah.
you know, because
Okay.
you know, if you think like, you know, nature is a hierarchy, right? And
Yeah.
each level has its description.
Right.
The point is to bind these levels together.
Yeah, so it then, like many of the other laws that we have, if you say there is a law but with a lot of buts, okay, then it's a law. But I would say a law has no buts. And if it has no buts, then it would law. So for example, I would say conservation of mass is a law. And there is no but unless you go to non-Newtonian mechanics and Einstein relativity theory. Okay, then it's not a law there. But beyond that, it's a law. You can write it under any conditions, equilibrium, non-equilibrium, for solid, for gas, for under gravity, non-gravity, whatever. Then to me, that is a law. And in fact, the Neville Stokes equation is a combination of a law and some approximations. And so that we'll get to that. So actually, almost all equations we know, they are not law. Darcy's law is not a law, Fourier's law, Fick's law, they're all approximations. The governing equations are a mixture of a law, conservation law, and some approximations, which we call constitutive equations. So in principle, the conservation laws apply to any material under any condition. Mass conservation, momentum conservation, energy conservation. You can also add angular momentum if you are interested in electromechanics. You can add the conservation for that. You can also draw a balance of entropy, which is not really balanced. But then they are valid for any material, gas, liquid, solid. So if you want to specify a given material, then you have to put in something related to the constitution of that material. And that's what we call constitutive equations, have to be added to that. So we use the averaging approach to derive the conservation laws. And the conservation laws themselves take different forms, or not different forms, at least have different terms in them, depending on the scale. You can have the scale of a molecule, or molecules, the scale of continuum, the first continuum scale. Then you can have a scale in the pores, in the grains. Then you can have the porous medium scale. Then you can go to the reservoir scale. I mean, there are all kinds of scales. And we can derive conservation laws. And we do that using the averaging approach. And then the constitutive equations, we use what we call a rational thermodynamics, or we call that the thermodynamics approach, that basically makes use of those laws plus entropy, second law of entropy, thermodynamics, entropy inequality, to derive constitution law. Often in physics, constitutive equations have been proposed. I mean, Darcy's law was proposed. It was not really derived. And a lot of other laws were proposed. But here we can derive it, and by doing so, we unravel all the assumptions behind that law, and therefore when it is valid, when it is not valid. So we have these two steps, and the first part of the lecture will be the first part about going from molecular to larger scales, and then the second part I'll introduce this thermodynamic approach. So we start at the molecular scale, where we really have the least number of assumptions and idealizations to make. By the way, please do interrupt me if...
In kinetic theory, kinetic theory gives an explanation of the derivation of the Neville Stokes equation from the conservation of momentum. And the Neville Stokes equation corresponds, you can derive a hierarchy of equations for the Boltzmann equation. And then the Neville Stokes equation corresponds to the first step in the hierarchy, which is coupled to the next terms in the hierarchy. And then this is the approximation made in the framework of kinetic theory, which corresponds to different time scales. You can introduce a relaxation time at each level of the hierarchy, and then you cut, you make a closure of the hierarchy, you obtain the Neville Stokes equation.
Definitely, yes. So there are other approaches to derive the same. For example, Neville Stokes equations. I must say I'm not familiar sufficiently with kinetic theory. In fact, from there you can derive concept of temperature, pressure, viscosity. They all can be derived. I wonder whether you can do that, for example, for multiphase flow in porous media. And then what is, to me, different here is that we make this separation between conservation laws and constitutive equations. And that's what I also like very much, because as I said, we can then derive conservation laws for multiphase flow in porous media with interfaces in there between the phases and with any other effects in there. And that's and then add later on
And
constitutive.
to propose a constitutive equation, you must know all the variables included in the functional form of the constitutive equation. No? You must have information about.
Right. Now, I hope there will be time that we go through it, and I hope you will have a chance to see that part, and then we can talk about how we do it, of course, yes. Okay, so the behavior of a material at a given scale derives ultimately from its structure at the lower scales. And we can say that at the fundamentally everything has a discrete nature constituted of particles. And you can go down in terms of what these particles are to, positrons and electrons, I don't know, all those elementary particles. But we are going to start at what constitutes a material. We identify materials with their molecules. So we say we start at the molecular picture, and we say that the material is made of these discrete particles that have a temporally random and very fluctuating motion. And the question is, can we link our continuum description to this very discrete nature? So let's say we have a material. I must say I'm not doing it as axiomatically as in mathematics they do it. Now, they has it in his papers, but I try to do it, for myself, simplified fashion. So we have a system consisting of a set of fundamentally discrete particles. We call them point masses. Those who have done lattice-Boltzmann modeling or smooth particle hydrodynamics, it's a little bit similar to that. Those are bigger particles. These are really molecular scale we start. So a particle Pi, so the system is made of many particles, indicated by Pi. I goes from 1 to n, and then total number of particles in the system. A particle Pi has a mass mi and a position vector. The mass mi we assume to be constant in time for a given particle. Particles potentially could have different masses, so that's why they have the index I. And they have position xi, which is a function of time. It's changing very enormously as a function of time. By definition, the particle therefore has a velocity that is defined to be the time rate of change of the position. Okay. So these are I have already introduced two things, mass and position. That's it. Okay, the rest is coming from that. For example, velocity is coming from the position. I need to introduce one more thing, and that is the particles exert forces on each other. And these are attraction or repulsion forces. Fij, force that particle I exerts on J, and is negative of particle J exerting on I. And these are not the forces that when particles hit each other. That's not what we mean. These are simply, say, short-range forces from distance, however. And then there are long-range forces acting on particles that are coming from outside world. Now, think of gravity or electromagnetic forces.
Sorry, can I mean, that the forces are pairwise additive is an assumption, and many of the problems in transport on a molecular scale come when you have, for instance, non-pairwise additive forces close to a wall.
You're assuming this equality.
Well, I mean, if you have pairwise forces, it's fine, but if you have three body forces or many body forces, then you can no longer say that. Newton's third law is not nearly as important as the first and the second.
Right. It's not strictly necessary to make this assumption. Okay. Absolutely right. But I think, as I said, I want to keep it reasonably simple. Okay. Now, the conservation laws for molecular scale. We need that too. So what's the conservation law at the molecular scale? What do you think? What should be the conservation law?
momentum conservation?
No, not momentum. Conservation of mass, I'm sorry. What's the conservation of mass at the molecular scale? You are usually used to some differential equation when it's a conservation law equation, right?
Yeah, if two particles they collide, then the mass before and after should be the same.
Exactly. So the mass of a particle is constant, doesn't change, as I said, with time. So that's the total number changes. No, this is only for non-decaying material. So the total number of molecules in the system remains constant, and non-decaying, and then closed system, of course. And yeah, that's it. So the mass of a particle doesn't change, and the total number of constant. That's the conservation law. I don't think we need anything more, right? Okay. Then for the momentum conservation, we use Newton's second law, and the Newton's second law says that the motion of actually here I put in MIDI, I could have put in momentum instead. Show this with one symbol called momentum, that's PI. And the rate of change of momentum is as a result of force acting on it. And for particle I, that momentum change is as a result of forces of all particles around it, plus that long range force on them. So this is for a single particle. Okay? And this summation is over all particles. So these are actually my starting points, and everything else then will come from this. All right? So we want to upscale, go to the first continuum level. Now, one of the first concepts we introduce is mass density. We are very much used to that, and we define it as the mass per unit volume, but then we also have to define a spatial point. So at a given spatial point where we make our observations, what is the mass density is the total mass divided by volume. And then you can ask, okay, which volume, which total mass? You need to define that. So there are ways to do that. One way is to say, I have a position X, I'm sorry, this is a small x, not capital X. Yeah, it's a small, you can see from the size, from the shape. So that, because it's a vector, so it makes it fat and bold-faced. So this is a spatial position X. We put a volume around it, now a cylindrical space around it, and we say in this volume, the total number of molecules divided by volume is the mass density. And you can ask, total number of molecules, the molecules are coming and going. You are right, so we have to take an instance, one instance, and that instance, we count the number of molecules and divide by the volume. And that is shown here as the mass density is right here, okay? Simple. But then you can say, I'm measuring mass using an instrument that, and I can give you an example. Now this is in case of mass, but in case of some other things, for example, concentration of solutes, I'm measuring an instrument, and that instrument doesn't have these sharp boundaries. Measurement window doesn't have these sharp boundaries. It's, measuring some volume, and in fact, the particles which are in the middle, it measures even more of them, or they are making more effect on my signal than those which are farther away. It actually has a big observation window, which the strength comes for more in the middle, so it doesn't exist in my instrument. That's right. So then we really should have a more general measurement window, which is really basically counts all molecules of the system, not only the ones near this, but all of them. It's just that it gives different weight to the mass of those molecules that are farther away or closer. And each time we do this at a given x, and then we can move this x, and then there is another. So this is a weighting function. And now we make the definition of the mass. By the way, so this weighting function must be such that if you integrate this over the volume, so it has values here, and this is much less than 1, of course, so that the integral is simply equal to unity, is 1. And with this weighting function, then we define mass density in this fashion, where we sum over all molecules, but then we change the position where we evaluate psi. So that means that at a given position x, we put this psi and say, okay, the particles that are here get this weight, and those who are here, they get a smaller weight and smaller weight and smaller weight, and that gives me mass density. And so we look at position x, it's okay, where is this particle compared to this? And that gives you psi multiplied by the mass. Okay? Is that clear? So this is a mass density which is really linked to the concept of measurements, because now each instrumental measurement will have really its own psi. And potentially, using different instruments, you may get different masses. No. That's why we assign this subscript psi to indicate the fact that the average quantity you are defining depends on the psi you are using. Okay. Now, we also then define a momentum density function, which is the average of momentum of molecules. Each time we define the average of a quantity, we take that molecular quantity multiplied by psi and sum over all molecules. That's the averaging procedure. Multiply by psi and sum over all molecules. And the momentum, as I said, is MIVI, and you sum all of them, and you get the momentum density function, which is the total momentum of molecules that are centered around point x, spatial point x, and divided by the volume. Okay. Please note that if you ask where is the volume coming from, division by volume, you don't see it because psi is 1 over volume. Okay. Then from macroscopic velocity is defined to be the momentum density function divided by rho. That's the macroscopic view. And that is what is really measured by various measuring instruments that measure velocity. It's important to realize that because you could have potentially said, I define average velocity or macroscopic velocity to be V average. No, I put this sign bar on it or so to average, is the sum of all individual particles. And you can multiply it by psi if you wish. Right? That's also average velocity. In fact, in statistics, don't we always just take average of a million numbers? You just add up the million numbers divided by million. But this is not a physically meaningful average velocity. If the masses of different molecules are different. If the masses are all the same mass, it doesn't matter, then it's okay. But potentially the molecules can have all each different mass, then this is a wrong definition. Why is that the wrong definition? Any of the students would like to?
I wanted to ask why this is the right definition.
Yeah, right. Okay, let's say I use this we do it the other way around. We do this as the definition of average velocity. So you have an average velocity, and you have an average density. And that's it. The thing is that we want to define everything at the macroscopic scale, the average scale. And once you are at average scale, you have absolutely no information about molecules anymore. Because we don't want to work at two scales. Okay, you are at average scale. This is your average velocity. That is your average rho, I just defined it. What is the total momentum?
It will not be the same if you use this averaging for the velocity. You will not have the same momentum if you sum them up from the molecular level or using the average.
That's exactly my question. So that's my question. This is your velocity. You have a rho. Your fellow students ask, oh, then the momentum of this system is rho times v, right? Oh, he said it then. That rho times this v doesn't give you the momentum of the system. The momentum of the system is this. And that is not equal to rho times v bar. You have something else. So this is definitely an incorrect in the sense that it doesn't really give you the momentum of the system. So velocity at the macro scale, and in fact maybe that's what I should have done, that actually they can undo that in their book. To go back to the original, and then it's better, is to define not the velocity, but to define momentum. To say a particle has a mass and a momentum. And then the velocity would be shown to be equal to this, and is equal to the momentum divided by mass. Now then you can see that momentum is actually, velocity is actually not a primitive or a, what's that, primary concept. Position and momentum are primary concepts. And velocity is a derived one. And if it's a velocity derived one, is that VI is momentum, that's PI divided by MI. If that is what velocity is, you must observe this definition at all the scales. Momentum, total momentum divided by mass.
This definition, if the mass is equal to 0, the particle could have velocity.
If the mass is zero.
If you define the velocity in this way.
Oh, that's correct.
And then if the mass is 0,
yeah.
VI is not necessarily 0 from this equation.
That is correct.
The other definition, it is 0.
That's correct.
I mean, is the point here that you should average over quantities that are conserved?
That is.
That means P and M.
Right.
If you average over V and then try to construct a momentum from that, that won't be conserved.
That is correct. So actually, there are, I think I'll come to that. There are 4 criteria for defining averages at one scale based on another scale. One criteria is that the definition of the thing that you are averaging, whatever you are averaging, and that's here, let me go back to it. So whatever you are averaging must be a physically identifiable and therefore conservative concept. What is VI times psi? Remember, psi is 1 over volume. What is velocity divided by volume? You are summing velocity divided by volume. That's not summable. So that's not additive. Must be additive. This is not additive. That is additive. That's the momentum of this plus momentum. You can add momentum. And the same for mass and energy. So that's one of the, and I mean, such a, to me, simple concept. But if you look at the averaging literature in porous media, they are full of this kind of errors. And I'll come back to this later. Okay, so that's one of the things. One is that it must be something that is additive. There's another criteria for defining averages. Averages, we are defining macro scale concepts at a new scale. And these should correspond the way we observe things at that scale. We just don't sit here in a class and then behind our desk model the outside world and that's it. Then the outside world should follow us. No, we have to observe the outside world and then model it. How do I measure velocity? You gave me the majority of instruments that measure velocity, they measure momentum. They are hit by something and that is added up to something we measure. Take, for example, a pitot tube. A pitot tube, they put it in a flowing water. The water hits the opening of the pitot tube. By its mass and momentum goes up the pitot tube. That's what you measure. So it's mass times velocity you're measuring. So whatever you define must correspond to what you are going to in reality measure. And I've given you many examples of it. Okay, one example was the use of psi. If that is really in reality, you never measure the number of the mass within a given sharply defined volume. No, then that's not the way to define mass density. Okay, so with these definitions, now we are ready to derive balance laws. To derive them, not just to propose them, but derive them. We propose them at the lower scale, the molecular scale. So to derive the mass balance equation, what does mass balance equation mean? What does mass balance do? The mass balance equation says, how does the density, or the mass density change with time? That's what mass balance equation says. Okay, so let's look at that. What is d rho dt? That is what we want to know. Well, you remember the definition of rho was the sum of mi times psi. That was the definition of rho, is the sum mi. Why doesn't, sorry. So mi and then psi. Okay, this is rho, and d rho dt is just put the d dt of this. Now, remember, mass balance at the molecular scale says n is constant, the total number is constant. So d dt of this, I can simply move the d dt out inside the summation sign. Mi is constant, so I can move that here too. I only get d dt of psi. Okay? And now I get the time derivative of this. Now this psi is a function of t. Actually, it's a functional of t because it's not the direct function of t. It's a function of t through xi. It's called a functional. And to determine its derivative with time, I have to use chain rule of differentiation, which means that I write that is really d psi, d its argument, and then d of argument dt. That's the chain rule. Now, d psi dx, that is gradient, we call it gradient, material changing as a result of change of a spatial position where it is evaluated. So that is gradient, and this part, x and time are independent variables. X is a position, you fix it, that's it, and let time pass. So this means it will only get minus dxi dt. What is dxi dt? It's velocity. That's how it was defined, or we can show that it's velocity. Okay, so we put in velocity, and so now I have this, but this del can now be moved all the way out because mi is not a function of a space, vi is not a function of a space, so del can go to the, and then n is not a function of space, can go out here. And I get this. Now, I hope you recognize this. We just defined it, is the momentum, total momentum. MIVI multiplied by psi. So that's total momentum. or momentum is rho times v, so we can derive the mass balance equation. Okay? And you can say, yeah, big deal, I knew that. I learned it at high school. Yeah, that's true. But the nice thing is that if I could do this right in this fashion, maybe then I can do it if my system consists of many different molecules. And like in a porous medium, multiphase flowing porous medium, that they behave differently. And I have regions where the molecules have different interactions and so forth. And maybe we can do the same there. And then that would be the power. Okay? Questions? Okay, so I derived the macroscopic mass balance. I should have been more careful with the concept of macroscopic, microscopic, mesoscopic. So here, because these are all relative, at this stage, I defined molecular scale and one scale higher, that's the macroscopic or continuum scale. Yeah, but also continuum has many scales. Okay, the first continuum scale maybe. Okay, and then we want to derive the linear momentum balance. I hope you remember the momentum balance. I used to put them on the board. Maybe I can do that here, except that those in Oslo may not see it, but that's okay. So I remember, if you remember, I wrote that mi dvi dt is the sum of all forces acting on ij, and then this I j not being the same as I, plus bi. This was the momentum balance for a given molecule, particle. We multiply this whole thing by psi, and then average over all molecules. And that's what is now on the board. We multiply by psi and average over all molecules. Okay? I have put in the psi and the average psi. No, I have here moved the. No, nothing I have done. I just actually did what I just explained to you. Yeah. So I'm going to take the next step. I will take the first term in here. I take the first term on the left-hand side, and I use the chain rule of the differentiation again, because then the chain rule will means that instead of this whole thing being a function of time, is no, it's not chain rule. This is the product rule. Sorry about that. So the product rule says that the time derivative of this part, which is only of this part, I make it of the whole part minus the time derivative of the sine. So it's the product rule. So that's I told you, I make intentional mistake, and the idea is that the audience will tell me, yeah, but look, that's not chain rule. And so nobody has done that in the previous sessions. So I applied product rule. I have to change that. Okay. So then we do that. Now, the first one, time derivative can go out, and I'm left with this. And the second one, again, I apply chain rule of differentiation, and the chain rule is just like I did it for the mass, will give me the gradient of psi and multiplied by velocity, multiplied by dxi dt. So that is vi. So that's result of this becomes this because of chain rule. So that means what I have here is the time rate of change of the momentum density function, and what I have here is really the average of mi, vi, vi. Because mi, vi, vi is multiplied by sum, psi, and summed over all particles.
Is the change from normal derivatives to partial derivatives? I mean, you didn't discuss that. The first derivative is not a partial derivative.
Yeah, so the partial derivative and normal derivative are different by saying that when I do partial derivation, I fixed something. Now, we start with ddt, we could have written partial derivative. It doesn't matter, because when I wrote here, I can write partial derivative.
Well, then it's okay.
Because this is also keeping x constant, but it's just not relevant for velocity because velocity is a function of x. Yeah. Okay, so we need to do something about, see, this is now a macro scale quantity. We define in 10 momentum density function relates to average velocity, average density, so it's a macroscopic. What kind of macroscopic quantity is that? That's not clear, so that we have to figure out. Yeah, so maybe I do that because, you know, we have these other terms, we still have to define the averages, average of intermolecular forces and average of the external forces. But before we do that, let's attend to this term. We want to also write this in terms of some macroscopic quantity. Now we do the following trick. We define what we call a notional thermal velocity. It's also called deviational or deviatory velocity. We say each particle has its own velocity, but it is deviating from the average velocity of the material. So I define a deviatory velocity. That's defined in this fashion. Now, with that, I can find that the average of this deviatory velocity is 0. Because if you multiply by psi, sum over all molecules, you will see that multiply, by m and then by psi, multiply, you will see that the average of this is simply the momentum density function, mi vi gives you momentum density function, and the average of mi v psi is also rho times psi, which is the momentum density function, so it's 0. So the average is 0 of the deviatory velocity. You should expect that. This is in the statistics also known. Okay, but how about the average of the product of vi? Now, what we do then, we use the definition I just introduced, which is vi is really vi hat, plus v psi, vi hat plus v psi. I use that definition. For vi, I substitute that, so I get vi hat plus v psi times vi hat plus v psi. When you multiply 4 terms, these 2 terms, so vi hat plus v psi times vi hat plus v psi. When I multiply, I get 4 terms. Well, actually, I get 3 terms. I get vi hat times vi hat, then I get v psi times v psi, then I get plus 2 vi hat times v psi. Now, that part, vi hat, I have repeated here. This part, which is v psi times v psi, its average simply gives me this. And the part of vi hat times v psi, its average is 0. And I invite you to figure it out for yourself. So that means that one gives me these 2 terms. And this one is now a macroscopic quantity that relates to the fact that molecules are moving at lower scale, but I don't see that at a larger scale. If I have here a glass of water, and this water has this average velocity, because V psi is the average velocity here. So if I don't move and it's really steady, what is the average velocity of water here? It's 0. It's not moving, right? But of course water is moving. We just said particles are zipping around like hell. So there is something there that I can't observe. There is some momentum there I cannot observe at my macro scale. That's this one. That's the momentum exchange between molecules that is happening at the lower scale. And that is what we then, we know it's there, we don't see it, but we measure it as something else. Velocity, pressure, temperature, that's actually in here. That's what gives us things that are happening there when even it's not moving at our upscale of observation. So that's that part here. Now in this case, we are talking about, I don't know what this other integral doing here. Let me remove that. I hope I can remove it. No, I have to go to lower scale to remove it. That is this scale. You don't see it, I think. Yeah. Okay. All right. So we denote this with a symbol. This is a new symbol. It doesn't exist at the lower scale. It's a macro scale symbol, and it really quantifies some subscale happening that at our scale we just see it as one whole thing, and we denote it by this D. And that is the subscale transfer momentum among the molecules is non-zero even if the velocity of the whole thing is 0. So now we go back to our momentum balance and see where does this go. So if you go to the momentum balance, the first term therefore is written really after going through the procedure I just showed you. I get the derivative of momentum, I get the divergence of the momentum transfer or momentum flux, and I get the divergence of this term. And then I look at the other forces in the other terms in the momentum balance. The intermolecular forces, they affect in each other, and I find an average force interaction among molecules. Now it is interesting to note that if you take a, for example, a sphere, all the molecules that are within that sphere, they don't have any exchange with each other because the sum is 0. Only the molecules have exchange with the outside the sphere, the one that hit the sphere, and only that will survive. So actually, this is a surface force. It's not a body force. Within the body, you can always have that. We only have a quantity if you put a surface through the material and you say, okay, the molecules on this side exert forces on the other side. That's one here. And this is a body force because this is coming from the outside world. All the molecules feel that. So there is really a major difference between these two. We write them like this, but this is very different in nature than this. Okay? Now, then we can show that this has been also mentioned in the work of actually there is a derivation for that in a I think by Noel he made a derivation, and you have it in your papers, that you can show that this vector is the divergence of a tensor. And it is by the virtue of the fact that it's a surface force. And so one can go through that.
Erwin Kirk would also show that.
Oh, okay. I mean,
The null also.
yeah, I think I knew about the one by Noel. So if you put that now in here, then you notice that you have a divergence of this T prime. We have a divergence of D. So in terms of equation, there is no way you can distinguish between D and F. They go together, and therefore we define this total force, which is T prime minus D. That is a stress tensor. Now let's have my momentum balance equation. You have seen this before, right? But now at least you can see that the stress tensor is a combination of the attraction repulsion forces between molecules. That was the F part, and the fact that molecules hit each other. That is the MI, VI hat, VI hat. They hit each other, and that causes, we measure it, we experience it and observe it as stress. And in fact, that is the source of pressure. Because pressure in a fluid, or in a liquid within a gas, pressure is the state of stress when there is no movement. And then so when there is no movement, the state of stress, and when it's a movement, that means macro scale movement, is that hitting of the molecules with each other. Okay. Yeah, and I think maybe we can do this little exercise to see this, what I just said, what pressure is. But maybe we should take a break first. It's been an hour. I'd like to do that. Maybe I explain the exercise and then we take a break, and then I would like to leave this to you to do the exercise. So the exercise is the following. Let's say I have a cylinder, it's confined, there's a piston here, and there are molecules here. Nothing is moving, the piston is stationary, this whole thing is stationary. So the material is at rest. The average velocity is 0. What are the forces this piston is receiving? And the sum of those forces. And what do we call the sum of those forces, by the way? What do we call them? What is this piston, the force is receiving, we call it? Pressure. So what is that pressure? What is that? And that's what we want to calculate here. Okay. So we take a break. Is there a possibility to have some tea or coffee for the audience so that... Yeah, okay. Let's do that.
The idea is to construct a discretized hydrodynamics. No? You can discretize the hydrodynamic equation by using the representation of the gradient of a function in terms of an interpolant. You can write it in an integral form. And then from this integral form you can discretize the hydrodynamics. And the discretization is more useful for simulations.
Okay. By discretization you mean localization?
No, I mean you divide the system in pieces, in parts, and then you analyze particles, big particles instead of elementary particles. And you can write down all this equation for that.
You don't mean like finite difference, finite. I'm just trying to understand what is it exactly you are referring to. You don't mean finite difference, finite element kind of discretization?
Discretization means that in your particles, contains many particles.
Oh, okay, yeah, like SPH.
SPH, for example.
Yeah, well, they work with that indeed. That is not my purpose here. No, my purpose here is to develop a continuum description, like the one, because now this
I know, but this continuum description is related to the discrete description.
Discrete, yeah, that's exactly what I did. I started from the molecular, the particle description. Now, in my case, the particles, I consider them to be molecules. You can take them bigger mass points. That's true. If I understand your comment, please help me.
We can discuss later.
Yeah, okay.
If you want more water, we can
Let's
go.
get some more water. Okay, so let's continue with this exercise that I want to know, basically show the fact that this D term that I just came up, which is rho V. V is really translates into pressure when at the macro scale we make observation. So if you have a piston here, now say pressure is force per area, and the force that is receiving here is as a result of the momentum of particles, and actually the momentum change of particles. Change of momentum per area is the force. Now, so if you take a molecule, this molecule over this distance that comes and with a velocity hits this surface, its velocity becomes 0, because at the moment it hits here, the velocity is 0. So from a velocity v, and of course velocity changes with time, but let's say you work with an time average velocity, and that's another issue, we come in a minute to it. Everything we talk about average, it doesn't happen instantaneously, it happens over a time period. So we really have to do a time averaging as well. But okay, so there is an average velocity hits here, becomes 0, and then becomes v again. So that means the over a period of time where the particle goes back and forth in that space, and the time is 2L divided by its average velocity, its momentum changes by 2 times mvx. Because it was mvx, became 0, and from 0 becomes mvx, and went back. So therefore the pressure is that momentum exchange, a momentum change divided by time, and then divided by area, and that gives you mvx squared divided by v. This is for one particle. And then if you sum this up for all particles, you sum this up for all particles, and then because in this case we assume all particles have the same m and the same vx, so you simply multiply n times m, and then the average of vx, you remember that vv average, rho mvv average is this one here. So the average of this is the summation means, and that is what we call pressure, because it's, I put the v on the other side, make the summation, and that is pressure. So it's really related to the average of deviatory velocity. Why is this deviatory velocity? Because the average velocity itself is 0. So this is v. You can write it like that, but you can also write this as, oops. You can write this as the sum of mi vi hat vi hat, but then the scalar part, and times psi. That's exactly that term, which I had it earlier as D, capital D. So that's what we observe as pressure. It's part of the stress tensor. Okay.
So, the pressure becomes a tensor here? Or?
No, it's not a tensor, because each time you have to take the inner product of the velocity and the surface. And so if the particle moves parallel to the surface, it doesn't exert any force. So you have to take V dot n of the, so that is really V dot n of the surface. So these are all scalars. We're only taking the component of the velocity that is normal to the surface. So it's done in a very crude way. We can do it as accurately as you want it, but the gist of it is just to show that the pressure a transducer measures, a transducer has usually a sensitive surface, and that is simply the molecules hitting and going back, hitting and going, that's pressure. That's what is measured. That's it shown here. And similarly, but then seemingly totally unrelated to this, temperature, or the heat, is if you have a thermometer, it has a sensitive surface, molecules coming and hitting and going back, they give energy to it. Then it would be the same, except that it's 1/2 of this. And some people say, oh, well, this is temperature, but it's not temperature, this is pressure. This is related to force. And when you put the 1/2, you will see that's energy, that's different. Okay? All right. So we can do a macroscopic energy balance at the molecular scale. Molecules, we already said that they have a velocity, they have a momentum associated with any mass with the velocity is a kinetic energy, which is a momentum and its inner product with the velocity. That's the kinetic energy. You could assign to any of these particles, we started with any of these point masses, in addition to its translational velocity, you can also associate with it other motions, like rotation, vibration. So you can say each molecule has an internal energy itself. Let's not do that. So we simply say, okay, a molecule is zipping around. That's all motion it has. So if that's the only motion it has, to get the energy balance, we take our momentum balance, this is here, the momentum balance for a particle. We take its inner product with velocity, and then average over all particles. Now that gives me my macro scale energy. So I have taken that term, this equation, multiplied by V dot, that is this one here, multiplied by inner product with V. The other two terms also, I changed the order here. And multiplied by psi average over all particles. That's my macro scale energy balance. Now, it's not useful as it is written here, because I need an energy balance in terms of macro scale properties. You remember, I had average velocity, average density, a stress tensor I defined, an average external force. I want those in my balance laws, that kind of term. So this is not, I have to convert it to those. So what do I do that? Well, we are going to use the trick we had before. Say, okay, velocity of a particle is a sum of, you can divide it into, decompose it into an average velocity of the whole system plus a derivative velocity of the particle. And we substitute that in here. Now you get lots of terms, and then we are trying to see, okay, what are those terms telling us? What are they? So for example, if you take the first one, and instead of VI you write this, and then what do you get? You get two terms. Each time I make use of the fact that, I make use of the fact that, the average of a macroscopic velocity quantity is itself. The average of V psi is V psi. It's an average quantity already, is it? The same for all molecules. You sum it over all molecules, you get the V psi back. So that's why when we put this in here, that V psi can always go out of my summation sign, out of my averaging operator. So that means when I do that, the V psi goes out, and the sum of Fij psi's, I already defined that earlier for momentum, that's F psi.
Sorry, I have one question. I mean, implicitly, I think you now assume that the velocities are uncorrelated with the forces, which in equilibrium is fine, but if you do it more generally, then that might be a problem, no?
Which velocities are you talking about? The
VI?
average velocity or VIs?
Let's talk about the VIs.
Yeah, the VIs, they don't have to be uncorrelated.
Okay.
They don't have to be, because I don't make any assumption about VIs other than saying that I decompose them into the average velocity of the system and some deviatory velocity. And this could be still correlated with F or whatever you wish. It only says that it's only a function of time. It's not a function of where the particle is. That's the only assumption there. Because V itself is only a function of time. Okay, and then the V psi is a constant goes out, and that I can do that mathematically, and whatever remains when I do that, it's called F psi. That was defined already, the sum of Fij's times psi without E. The other term we had remains, survives. It's here. Okay. And of course, you recall that I had shown that, or I had assumed that I can show that F here is del dot T prime. So I can replace that with F dot D prime. What is this? This is, let's say, the same glass of water. The water is at rest, but there are forces between molecules, and they are moving. Except that I don't see any of that at this scale. But inside it's happening. So these particles are exchanging work. This is work. They are exchanging energy. They are exchanging work with each other. And that should show up in some way. If the molecules move faster or slower, this should change therefore. So what would that be? What do you think?
Temperature.
Is exchange of energy. What do we call exchange of energy in a system where there is no movement? I don't see any movement. What is possible exchange of energy?
Heat flow.
Heat.
But that is not necessarily work.
It's not macro scale work, but it's definitely micro scale work. It is not only, no, that's correct. It's not only work, but part of the micro scale work that the molecules do on each other when you put a surface through, imaginary surface, the molecules on one side, they are exerting force in each other, and that force is being moved with a velocity. Force moving is work. So it's part of heat. No, it's not the only thing we will see. There is more that constitutes heat. But that's why I already prime you that this is what will go into heat. Now let's take the second term in the energy balance equation. If you recall the second term, so that was the F term and then the B term. So B dotted with V and then average over the velocity. Now we do the same thing, which is writing at V hat plus V psi. The V psi goes out. The average of BI, we call that some macro scale B, like gravity. So that is the term here. So gravity multiplying average velocity of the system, that's the work of gravity. But we also have some subscale work being done on the molecules. The molecules are moving around even if the whole fluid is not moving, the molecules are moving around in this material. As a result of force coming from outside, there is energy produced or done. Work is being done by molecules in that force field. So we will remember that. And then I take a look at this.
Sorry, but in this case, I think that you assume that the external forces on different particles are different.
Actually, I assume them to be constant.
Can you go back down?
Because the strength is a strength. Oh yeah, actually no, sorry. It's different because I didn't take the mass out of it. For example, if I had written MI,
sure.
Then it would have been simply the strength of the gravity.
Sure.
You're right. It's not. It's different. Correct. Yes. Okay. And when I write it like this, actually, then I basically partly assume that. So I take now this other term. Now this is again the summation of MI, VI, VI, and then the time derivative. Now I use the, I can write that using chain rule as 1/2 of MI d t dvi, because of symmetry of velocity. And then I use the chain rule of differentiation, a product rule, to move the ddt outside and then subtract from it the time derivative of psi. Now this is this part here, so I get this term minus this term. Now this one, I do the trick of VI hat plus V psi, the average velocity. So that gives me again two terms. That gives me two terms. One is, before I do that, I use the chain rule here to write that as velocity times the divergence of psi, and then the divergence is moved outside because everything else is only a function of time. So I have, that is reduced to these. These are all still molecular forms. I have to convert them to macroscopic quantities. This one, you saw what we did in case of momentum. You replace this with V hat plus V psi. In case of momentum was a tensorial quantity, here is a scalar quantity. That gives me two terms. Here is more difficult because I have mvi squared vi, so that vi hat plus v psi multiplied by each other 3 times and then average of it. So it's really messier, but still we can extract things from it. So the first time, the first term, that gives you, and that's by the first term I mean this one. Right. Could be that I'm going too, what is it? Too fast here. Yeah. Right. So the first term here, maybe I'll do it here. That becomes the summation of I mi vi hat vi hat, or maybe I should even write it the way it's written as a square. So it is a scalar, so vi hat the square, and then plus mi v psi square. There is plus 2 mi vi hat v psi. And all of this averaged. Now, in this this one here, v psi is constant, goes out. I only get average of mi. That's density. Average of mi. In this one, vx goes out, v psi goes out, and I get average of vi hat. That is 0. I showed that earlier. So this becomes 0. This gives you rho times V psi squared, and that survives. And that is what is shown here. I get the time rate of change of this deviatory kinetic energy plus the macro scale rho psi kinetic energy, basically. This is macro scale kinetic energy, and it's flux. Oh, is here. The time derivative of kinetic energy. Okay? So if I'm at the macro scale, the balance law tells me you should be seeing a term related to the average movement of the material. But even if the material is not moving, you will have some kinetic energy, which is not visible as kinetic energy at the scale. Here, there is kinetic energy here. And that kinetic energy is that MIVI hat squared. That's what we call internal energy. So that term on the right-hand side, that's actually internal energy. And in fact, we know that if you provide energy, for example, heat it up, they can move faster, will go up. That's the temperature that goes up. So that's related to temperature. Now, then the second term with the divergence gives me this term here, but also gives me 3 more terms. And these are the terms shown here. MI VI hat squared, and then multiplied by average velocity, VI hat squared multiplied by VI hat, and then VI hat as vectors in a product with V velocity. If we go then further, as I said, we define this to be internal energy. And if we define a energy density function as the internal energy divided by density, no, then that whole written is as rho E. Is that clear? Does anyone wants to dispute this? Please don't take it for granted. Why is that internal energy?
There's no other energy.
Yeah, when we talk about this, what are the energies it can have? Kinetic energy, internal energy. The kinetic energy is mass density times average velocity in a product, and 1/2 of it. That's kinetic energy. But if it has anything else, that's internal energy.
Sorry, I still don't quite understand that point, because it is true that, of course, you have kinetic energy and the internal energy of the molecule, but you also have forces between the molecules, and therefore you have a potential energy of interaction.
Of course, but the forces between molecules goes into work. And the work has a macro scale manifestation in stresses multiplied with velocities, has also a manifestation of work that we don't see as movement and as a stress, and as heat. So the forces between the molecule goes into heat. But the energy to the amount of energy, say energy per unit volume.
Yeah.
Let's talk about that.
So the energy per unit volume then doesn't contain potential energy of interaction?
No. That is.
And chemistry is also for the time.
There is no, indeed, there are no interactions in here. This is very simple material. It's not decaying. There are no different molecules. There are only one molecule, say, or at least there are inert molecules. That's correct. Yeah, but the potential energy that you talk about, it's always related to the either the pressure or the gravity. And that is not internal energy. Internal energy in the sense that, let's say for a minute, I don't have any external force at all. So, what is the internal energy of this? It's the kinetic energy of the molecules that gives you an average velocity of 0. That's the internal energy. as I said, if the molecules also have rotational movement or vibrational movement, that will also contribute to kinetic, to internal energy. I could have put those as extra terms when I took this and multiplied with the velocity.
Let's not make it more complicated than necessary. No,
but potential energy is not internal energy.
But if you, okay, so let's, maybe if I can just digress for 1 second.
Yeah.
But if you take, for instance, a very simple equation of state for an interacting fluid, the Van der Waals equation, and you compute the internal energy, because there you know everything, then the A constant, which is due to the interactions, is there.
But if, let's say, you increase the pressure on the system,
Yes.
right? Now, then
you do work, and yes.
Then you do work.
Of course. I'm not saying the change in internal energy absolutely has to do with work. But if
they are related when you go to the energy balance.
Sure, absolutely.
In the energy balance, then you have, of course, term from potential energy and now heat flux and so forth. But in terms of the definition of internal energy,
Yeah, this is the point.
that's the definition of internal
That's the
energy.
definition.
The total energy of this system is the total energy. I can write it here maybe. It's simply 1/2 of mi vi hat v. Sorry, v. Not vi hat. Vi. So vi with an inner product, and then sum over all molecules. Is there any other energy at the molecular level?
I would say yes. If you,
Where?
for instance, have a crystal at very low temperature where you can ignore the kinetic energy, that crystal can still expand against a piston if there are Coulomb forces between the particles, and that can do work.
But is that internal? I
don't know. Maybe I should not monopolize the discussion.
Well, I mean, the internal energy is the expectation value of the Hamiltonian. And so that contains kinetic and potential energy.
Okay, but so maybe that's the thing. When we take just the simple picture of the momentum and the forces that are here, and I multiply this by velocity, I do not include those terms, and I could potentially put them in here.
Well, they are always
When I
somewhere.
add
It's compressional energy, basically.
But to me, the molecules are zipping around, and that's their only energy.
So, for example, the interface you have in water between the air and the water, that is not part of this internal energy.
No, that's the outside world. It's a closed system. I'm talking inside. The only energy I see for the molecules is the fact that they zip around.
The thing that is a definition of internal energy, you can define internal energy. There's a definition in the book by Landau and Lipschitz, in which he defines the internal energy as the energy of the system at rest.
At rest, exactly.
Absolutely at rest.
That's right. That's exactly what this is. And that gives you this VI hat, VI hat.
The point is that the heat and the work, they appear always combined.
They appear together in the balance law.
Yes.
So if you look at now, let's say go further, this is from the terms that I had here. So from the terms I had here, I call this internal energy. That's my macro scale kinetic energy. And now I look at these other terms. These are the flux of energy, internal energy and kinetic energy. Because if you look at them, this is the flux of internal energy, because this is internal energy times macroscopic velocity, and this is the no, let's keep that. Actually, let's keep that. I'll see it. So, therefore, I had time rate of change of what was identified as internal energy, kinetic energy, macro scale, then the flux of those two. We had this term in here, and then I identified there where the deviatory velocities multiply the macro scale velocity, the forces, macroscopic velocity, the deviatoric velocity is multiplied by that. And then there is all this term, which I show you here now, which I call heat flux. It is really the work done by the molecules on each other when they are at the medium at rest, macroscopic rest. That's that work. And the kinetic energy exchange between the molecules across an interface, across an imaginary surface. And that is heat. That's what we call heat. Exchange of energy between one part of the medium and the other part. And that has exchange through work of forces and through exchange of kinetic energy. Simply
normally in thermodynamics you separate very clearly between work and heat.
Yes, at the macro scale. And we did that too. This is the work at the macro scale. This is also work at macro scale. This is subscale work. We don't see it when it is at rest. And that's what is heat. So heat is, once again, the fact that the molecules come and go. For example, the piston I showed there, and we say that these exert a pressure, but they also transfer energy to that piston. And that energy is the kinetic energy hitting them and going back. That's energy. And if you put a surface not to be piston, but an imaginary surface within the medium, they also exert force across that surface with each other. And there is, because of movement, there is work. So that's also energy. All at the subscale. And that's what we call heat.
I think I'm missing the definition of some representative elementary volume. Because when you introduce that internal surface, then that should belong to something in order to have work well defined. You can't just simply introduce a wall in the middle of the system.
It's not a wall, an imaginary surface where the molecules on the two sides of it still interact. So we are not talking about molecules interacting with the wall. It's an imaginary surface where the molecules across the surface interact with each other. How do they do that? Through that, through this kind of interaction. Look at all of these have a divergence. A divergence you always can translate into a surface force. And what are the surface interactions? This is average velocities. So if I say the system at macro scale is at rest, this is 0. So system at rest, that is 0. This is 0. The molecules on the two sides are exchanging kinetic energy. That is heat. The molecules on the two sides are also exchanging, no, sorry, this is 0. This part is 0. So that's the only one remaining. In addition to this, we also have this force here. And I am afraid I didn't put that in here. And that is when you take, I put it on the board. Yeah, the Fij and then multiplied with Vi, and then you have a Vi hat here. So the system as a whole is at rest, so that's the only thing you have. And then you take the inner sum this over all multiplied by psi. Now, system is at rest. You have an imaginary surface. This is forces acting on the particles of this side, on the particles of that side, and it occurs that this force moves back and forth because there is a velocity. So that is work done across the surface. And work across the surface must be included in energy and will definitely increase. For example, if you think of temperature, when you increase the velocity, that means this work will increase. No, that's heat. You supply heat.
There is a microscopic interpretation of heat and work. If your system, if your energy levels are discretized, as happening in a quantum system, there are two ways to change the energy. One is to change the population of the levels, and another one to change the location of the level.
Correct.
Right?
Yeah. No.
To change the location of the level, you can do it by application of an external force.
Right.
This is related to work, and to change the population is related to heat.
Correct. Yeah. So, if you look at all the forces that I had in the energy equation, I identify macro scale terms that are like internal energy and this kinetic energy, and then the rest of it that I cannot identify at the macro scale, all the subscale exchanges, they either relate to the work of, so it is actually already macro scale here, this one. They relate to what we call heat exchange. Anything that I cannot identify when the velocities are zero, they still exist, that is heat across the surface. That's the concept here. And that gives me then this energy equation. What is it? Yeah, that gives me this energy equation. It's an energy balance. It says that the change of the total energy of the system is related to the work of macro scale forces. This is another macro scale force because if you recall, D and T prime together form stress, and then external supply of forces, the external forces, they also perform work because of macro scale velocity, and there is a term related to the external supply of energy that is not related to the macro scale motion or velocity. So all of that, and they all have definitions in terms of microscale or molecular scale quantities. Now, that all of that gives us the macro scale energy balance.
Let me add one comment because of Signe's question about the representative volume. The averaging over psi, the weight function psi, is what defines in your approach the representative volume averaging.
That's correct. Yeah. So you can take, as I said at the very beginning, the simple approach to say the representative elementary volume is a sharply defined volume around a point. That's simpler, and for me, I'm more used to that concept. That's my representative elementary volume, which does imply that macro scale quantities are solely based on what happens in that volume. Whereas, as I just explained earlier, there are measurement techniques that they don't have that. They get contribution is less and less and less from farther away. And that's why we put in psi, and now then the whole thing is a representative volume. It's a generalization of the representative volume, really. All right, so I think yeah, we can use mass balance and momentum balance equation and write the energy balance in this form, which says that the rate of change of internal energy, that is the movement of subscale movement of molecules, is related to the work of the dissipation, work of the movement of the liquid and the work of forces on it, exchange of energy, which we call heat, that is neither external force, neither work of forces, that's what we call heat, and then this is external supply of energy from outside world. Yeah?
That gradient of V is a kind of a strain, it is a volumetric change or deformation, it's a tensor.
Yeah, volumetric change is included here. This is not volumetric change, this is a tensor and multiplying another tensor
is a strain.
No, strain is included here. This is no strain, no. This is stress. This is the
That's
gradient
stress.
of velocity. This is a stress. This is gradient of velocity. Yeah. No, the strain is here. I can write a stress tensor as a function of the strain, and then I will multiply this. The del dot V dilatation, that's a different story. Actually, time rate of change of strain is not even a strain.
Yeah, it's
Del dot V is the time rate of change of strain.
It's a certain rate.
So, but that's not the same as here. So, if you had no flow, therefore stress is only pressure, then you get indeed that potential energy in here, volumetric change within the pressure field. Because then this becomes P times del dot V. This is a double inner product tensor. So Tij times dVi dxj.
Okay. Now, maybe I will, we can take another short break, but before that, if there are, first of all, any questions here. Up to now, I did an averaging, what I call a spatial averaging of the molecular properties to recast them into quantities and equations I can identify at the macro scale. And that's why I needed these concepts of energy, internal energy. I don't need them at the molecular scale. Stress tensor, I don't need a stress tensor at the molecular scale. Only I need to know is that molecules have intermolecular force and movement. That's it. But when I go to this scale, then I need them. And I introduce them, and I did that. That gives me these balance laws and the definition of macroscopic quantities. Now, as I said, any process you observe, there is time associated with it. And I said that these molecules move at enormously fluctuating time, so then you really have to say what happens if my observation occur over a time window. How would the definition of macroscopic quantities change? How would the macroscopic balance laws change? No, actually, fortunately, it's not going to change much, but we are going, therefore, to define time average variables. And you can do this in two ways. First, define a spatial averaging. And then, that spatial quantity, you average it over a time window of delta t, centered at the time t, and then divided by t. Delta t, that's one way you can do it. Or you could also define this actually to be 1 over delta t, average of t minus delta t a half, and then summation I1 to n mi psi, and then d tau. So that's another way you can do it. You can do it in one step. You don't have to do it the way I did it. I found it easier first to go to this concept of averaging and the link between micro scale and macro scale, and then introduce the time average. But this is also possible. So you could do this for the mass density, for the momentum density, and if you do this, that means you have to take all the equations I introduced and average them over time, the way I have done here. Do I get different form for the balance laws? Actually, I don't. First of all, I simply get yet another layer of these deviatory motions being added up. They were being added up in a spatial context. Now in time concept, they are going to be added up. So for example, my rho, macro scale rho psi v psi that was defined instantaneously, if I average it, it will give me a product of the velocities, but then a time average of the deviations. So, similar to what happened in the spatial case. Now you have that.
what is interesting is that even though A is a function of time, the average of the time derivative is the same as the time derivative of the average. There is no extra term in here. And the same holds for the gradients. These are identities. So with these, I go back to the, if I do the averaging, I simply get macro scale balance, mass balance exactly the way I had it with the psi, you remember? Except that now I have bar on top of the row. So the bar means it's average in space and in time. But the form doesn't change.
Can I just ask one? If
Sure.
you can go back 2 slides. I think it's 2 slides, sorry. Yeah, one more. Oh, E3. Yeah, no, sorry, that's the one. Your V of psi, initially you defined as the momentum density instantaneous divided by the instantaneous rho
Correct.
of psi. You multiply with rho of psi, so basically it's momentum density.
Correct.
But then you write this as rho average times V average.
Right.
And you would think it's rho V average.
No? Okay.
So then
No. Look.
say that it's rho V average.
This is 1 over delta t, t minus delta t half, plus delta t half, and then summation
No.
of mi vi psi.
Yeah.
So, on the first of all, I define my mass density. That you have no problem with.
No, not at all.
Then I say, this is the momentum of one particle. I sum it over all particles. And I look at this over a time. That is my total momentum density. And this total momentum density divided by average mass density will give me average velocity.
Okay, so that.
Right. And if I do not do that, then there would be indeed what was said earlier, the sum of, say, the definition I have for momentum density at the molecular scale and a later scale must be the same. The definition is that mass times velocity. Mass times velocity. At any scale, this should be the case.
And you can pass the rho bar to the other side, dividend, and then you would have rho psi divided by rho bar.
Yeah,
This is the quantity that.
yeah, but
Yeah, no, it's equivalent. I think that you are right.
yeah, no, that's the only definition, correct definition of average velocity.
Except that, sorry, I mean,
No,
I
sure.
totally agree, but it is not what naively you would call the average velocity if I have an infinitely massive particle and a very light particle in the volume. and I would use this definition, then what I get clearly, but that's already like you said, not the average velocity of those 2 particles.
Yeah, but that's exactly
No,
what
I-
we should get.
No, so
Because indeed,
sure.
indeed, if that's what we know, if you have a swarm of particles, and some of them are big, some of them are small, the average velocity is not just the sum of velocities divided by numbers.
Yeah, okay.
Absolutely not. That would be physically meaningless with average velocity. That's why you have to always take each particle and, oh, I just put it, yeah, each particle velocity multiplied by its mass.
Yeah, sure.
Add them up, that gives me my average velocity divided by total mass. Note that there's a volume here, so if I multiply this rho bar by volume, I get total mass. So total momentum divided by total mass, that's my average velocity. Okay, now I just want to show that the form of the balance laws won't change. The only thing that changes is now that the stress tensor that I had already introduced it as the effect of intermolecular forces plus deviating momentum balance, it is actually that deviating momentum balance, not only average in space, but also average in time. So that's the only definition that changes there. And the same, so the momentum balance doesn't change. It's the same as what it was. The form, the same holds for the energy equation. I haven't given that. It doesn't matter. Only the concept is that, for example, in case of energy and heat, if I have a imaginary surface, the particles across that imaginary surface transfer energy to each other, either through kinetic energy or through force, interaction force, and this happens not only instantaneously, but over a certain period. I have to sum all of that. That is the energy transfer, which is the heat. Okay. Now, the interesting use of this time averaging comes if you have a decaying material. Because in defining these time averages, I assume that the number of particles over this time distance doesn't change. But now if I have a decaying material, the number of n is not constant anymore. It changes with time. And therefore, when you do this average, you have to take that into account. And that will give you extra terms.
Yeah, and then in the second question, if you, as I said before, divide rho psi, and you pass this rho bar to the other side, right? You have rho psi divided by rho bar, and this is the distribution function, in fact. In the language of kinetic theory, okay. This is the distribution function, and the term on the left is the moment. It's the first moment of the distribution. So you are taking effect. Your variables are 1, v, and the energy.
Yeah,
and then you take the moment.
That way.
You reproduce exactly these equations.
That's correct. No, that's not put in here. And also, you can, as I said, drop this whole all together and only work with this, and then it would be mi divided by rho. Yeah, it's the same. Okay.
Is there a reason why you don't do the same with time averaging as you do spatially, with having such a psi function also for the time?
Oh, for time.
Yeah,
I haven't thought about it.
No, of course you can do that. There's no difference.
You're doing it. Sorry, this is a block.
Yeah, this
here is a block. Yeah,
this is a block function.
Yeah, that's true. But he's saying that why not making a psi equivalent of it here?
Yeah, that would mean it's cutting out all the large frequencies.
Mm-hmm.
That would give you a continuous distribution like you have for the psi.
Right. Yeah. But I really don't think the form of the equations will change. It's only that the concept of definition of this would be indeed having another psi multiplier. Yeah. But it won't change the equation. But it would be, interesting. In fact, there are instruments will probably do that. Yeah. Okay, so I think we stop here, maybe for 10 minutes, a short sanitary break at least, and then I will show that this time averaging allows me to derive decaying material balance laws. Should we start? Then we can stop maybe at 2 or so. Okay, so for decaying material, now you recall that this was the definition of rho bar, and for getting the mass balance equation for density, for mass, I had the time rate of change, and I could move, I could exchange the time derivative and the sigma. And so remember that this is the definition of rho bar, and the difference now is that, as I said, the number of particles is a function of time. It's not constant in this time period. So if I want to take the time derivative of rho, I cannot exchange the time derivative and sigma summation sign anymore, because this is a function of time. The numbers are not constant. So that gives me some extra headaches, but also gives me extra terms. So the time derivative of rho bar, this is rho bar in terms of the mass of particles, and But instead of moving the time derivative inside the summation sign, actually I do the following. Time rate of change of an integral in time is simply the value of the integrand at the two limits. So this is simply the value of the integrand at t plus delta t, and the value of the integrand at t minus a half delta t. And this is an identity. Okay, so I keep this here, and I show you later that this is related to the derivative of, to the divergence of mass flux. So please remember this. I'll come back to this. So now I introduce this notation that because we have a decaying material, that means there is some particles, so let's say particle mk, it has a constant mass for the time between some disappearing time and the initial time. Right? In that period, it has a constant mass m. At that time, it disappears, therefore its mass is 0. Okay? That's the definition of decaying particle. All right. Yeah?
If you go back to the previous one, you're using an integral there, but you have a discrete number of particles. You're using an integral for time. Shouldn't you use the sort of summation for time?
No, for time time is not discrete, time is continuous. At any given time, within my body, I look at how many molecules I have, where the molecule is, multiplies m with psi. Time is not discrete, time is continuous. So that must be integral, and then this is correct. So, with this means that, with this kind of definition, if I now look at the time derivative of psi and its integral, because that's what I actually need, previously I could easily move this into the summation sign. Now I cannot do that, so let me just, for the sake of my own exercise, look at this integral of the time derivative of psi, the weighting function. And then I do that in this time interval. Now, in this time interval, mk is constant until it disappears, and it's 0 after that. Therefore, this would be equal to, because it's the integral of the time derivative, f would be the integrand, this psi, at t dk, because in this range, mk is constant, then I can simply write it like that. And then minus the value at the initial time, and that is given here. That's also a mathematical identity. Okay? Now, then if I go there and now I sum that over all the particles and I integrate, so then means that there would be a number of particles that disappear in the time period between minus delta t half and plus delta t half. So that integral will give me all those particles, and then those particles who survive from all the way beginning to the end, they give me a term from the beginning and a term, minus term from the later time. That's again, you can write this as a mathematical identity. Now, I showed you earlier that this is exactly the rho dt. So this is the rho dt, which means that that term is d rho dt plus some masses that disappear in a given period. And the left-hand side, I can show that is del dot rho v. We have done this actually in the past. It's a matter of using the chain rule. Here becomes d psi dt, this side dx, and then dx dt, that becomes m times v, and that is definition of rho v. So that means with all of this together, my mass balance equation becomes this. When I didn't have a decaying material, this didn't appear, I only got that. And now I have decaying material, I have these things. And this I call the rate of decay in that period, and the equation for the decaying materials becomes this. Now, once again, there is nothing new. You could have, you already knew this, but once again, this is important to be able to do for more complex materials.
So, just, I mean, at the beginning, you probably sort of advertised mass conservation as one of the hard facts, but here you give up on mass conservation.
No, I don't give mass up. I keep track of the mass. And what I say is that I start with the mass conservation is this. I start with the number of mass, or a given amount of mass, and I end up with less mass.
But not through, you have the flux term, but that's not it, right? Because I mean, there's two terms. I mean, you say there's the things that flow in and out, no problem.
That's
and then the things that decay.
Disappear, and that is just the rate of decay.
But I mean, where does it go?
Oh, that you could say they become another type of molecule.
Okay.
And then you can write a similar mass balance for that other type of molecule.
But then
and then you will show that the mass that disappeared here is a production term there.
Okay.
And there you have mass balance. No problem. That's correct, yeah. Yeah, so you're right. In this sense, I said they disappeared, but of course, mass doesn't evaporate. It has to go somewhere. I didn't take that step. You're right. Yeah. Okay. Now, you can do this for the continuum, for the momentum equation, and for the energy equation, but in fact, for them, this reduced form doesn't change. They also have the, I think I have it in the notes, but there is a term here, but when you subtract the mass balance from momentum balance, those terms disappear. Okay. Now, this was easy, straightforward, in terms of it was all very simple mathematics involved and simple concepts. There are two difficult concepts. One is temperature, the other is entropy, because for thermodynamics we use these. We need to introduce them, and I must say I have no idea how to do by averaging, introduce entropy and temperature starting from molecules. The molecules don't have temperature. They don't have the concept of entropy either. They have things that lead to that, but not it. So the macroscopic processes, we know that they are often irreversible. With balance laws, we cannot describe irreversibility, because actually mass balance, yeah, you have a mass in this container, a mass in this container, you connect them to each other, they mix. No, mass balance will accept that. If you want to demix them, yeah, that's also mass balance, accept that too, no problem. The same with momentum balance. But that is not going to happen spontaneously by itself. And that is not described by mass balance and momentum balance. So if we connect a rigid ball full of an ideal gas to another ball which is under vacuum, there is nothing in it, and if we let this happen isothermally, so that means the gas from the full ball goes to the empty ball, and you don't say do not lose energy by heat leaving the system, so adiabatically and isothermally. No, then yeah, the total energy of the system doesn't change, but this process is not reversible. You cannot put things back to the containers without putting in something. So you really have to change that. And that irreversibility is not given by the balance law. Now about temperature, as far as I know, that temperature is a property that we introduce through the zeroth law of thermodynamics. That we say that two bodies that are, you put them thermally in contact with each other, and if one of them is hotter, this is feeling, than the other, they will have become equally hot or equally cool after a while, under equilibrium. And temperature is a measure of that coldness or hotness. So they will have the same temperature. They have the same thing, and that thing is temperature. Please correct me if you have a better definition of temperature. Okay. Now you can say that, okay, these bodies, they have that internal energy we described. You remember the molecules are moving around without any macro scale movement. They're zipping around in there. That's the internal energy. And when you put two bodies together, they all mix and zip around with each other, and that will then bring them to a same internal energy. And so if you say the internal energy is related to this temperature, but this is only an assumption, a linear assumption, and so it doesn't help. Okay. How about entropy? Now, to explain this, we really need to bring in the concept of microstates. If you have a certain number of molecules with given mass and velocity, that's a set of mass related to the molecule velocities or positions. But then we can have the same mass or same molecule at different velocities, with the average velocities being the same, but the individual ones are different, because the average, it's never the same as the individual one. So you can change the individual ones in infinite number of manners, whereas the average remains the same. So the same macro scale state can be given by billions of states possible. Okay, so what is microstate state? We talked that, explain that or describe that in terms of motion. I already mentioned the concept of translation of motion. They zip around. As I said earlier, you can also have that the molecules rotate. So that's another way of motion, and therefore energy associated with it. And they could be vibrating in the bonds, internal bonds. So that is shown here, that if you have a molecule of water, now this can translate as a whole, or it could be rotating around, actually around 3 possible rotation axes, or it could be internal vibration, and this is all energy. So when I derived internal energy, I only had that one. You could have added these as well, the energy balance equation. Okay, so the motion of molecules with a given macro scale property in terms of mass, energy, velocity can come from a myriad of combination of microscales. So each molecule has its own energy level, and that's what I mean by microstate. Translational, rotational, and vibrational state. They are at different levels. They could be more energy, less energy. So, as I said, a given macro state can be a combination of many microstates. Now, the thing is that there is more probability for some microstates to exist than some other microstates. For example, when all the molecules exactly behave the same, that being changed to molecules behaving very differently, observation says it doesn't happen. So it's more probable for molecules to achieve a state, microstate, that they all behave the same. More or less the same velocity, the same energy.
Sorry, are you saying that those microstates are more probable?
More
Or
probable.
that there are more microstates corresponding to the same macrostate under those conditions?
I think it's the second of it. Correct. I am moving on very slippery ground. These are, yeah. See, I promised to be very rigorous and very, but now I'm waving my hands. So let's, yeah, this I also got from the literature. So what it means that these are the molecules of a given material at a given macrostate, and that macrostate could have that this one or this one, where two of these molecules, this goes to a lower energy level, that goes to a higher energy level. Still nothing has changed. These are two different microstates giving exactly the same macrostate. Or you can also consider a situation that two different macrostates. This is at the higher temperature, this is at the lower temperature. The molecules are exactly the same molecules, number of molecules 36, but now these are at higher energy levels and different energy levels. So that's also different microstate, but also different macrostate. You can even say that there are various levels of energy. That's another possibility. So all of this saying that microstates are possible to be different macros for the same macrostate. So then we say, okay, well then macrostates are conserved, but microstates are not conserved. So we have now a new, how do you quantify this situation? Then we introduce a new macro scale property called entropy that's not conserved. Everything else was being conserved, mass, momentum, energy, entropy is not conserved. Accounting for these microstates that are possible to be very different, not conserved, and therefore we need this quantity for it.
I don't understand when you say that the microstates are not conserved. I mean, aren't the microstates or the energy levels, they are given, and then we speak about the distribution among these levels.
That is the microstate. So microstate is the distribution
But how
in
can
those
the
energy levels.
microstate be conserved?
Microstates cannot be conserved.
I mean,
But macrostates, so what I mean is for the same macrostate, I have many, many different possible microstates.
that I agree to.
Yeah.
So,
which means that in a given process, I haven't changed my macrostate, but the microstate changes.
the distribution among the states.
Right. That's what I call microstate. The distribution among microstate that changes. Right.
Yeah. I mean, velocities change when particles collide, but that doesn't mean that the energy of the system changes.
No, exactly.
Yeah. So that's the only
That's
issue.
the only
issue.
statement.
Okay. So if we say in a given process there was an initial number of initial set of microstates, at the end of the process there is a final set of microstates, then this is a pure definition. The change of entropy, which I introduce as a measure of how these microstates are, is a ln of that ratio. Other definitions are possible. And it is all really trying to explain or find a way of describing our observations. We know that experimentally that heat flows from hot system to a cold system and not the other way around. If we had observed that the other way around is also possible, we didn't need any others. But we know that, and therefore that's why we have to say define this entropy, and moreover, the entropy is actually related to the heat. Change of entropy is related to the heat, and through temperature. So heat, and then divided by temperature. And then you say, okay, useful entropy, but do you have an equation for it too? Say, well, that's easy. Remember those balance laws I derived for mass, momentum, energy? I have a balance law for entropy too. What is it? Yeah. Do you remember the mass, momentum, energy? They all had this form. Change of entropy, change of momentum, is some flux, divergence of flux. No, that's my divergence of entropy. Some external supply of that, like gravity, it was, or radiation, that's this term here. And it was equal to 0, the balance laws. And now it's not equal to 0, because we know it's not, it doesn't conserve. And that is the rate of net production of entropy, some gamma. And the second law says this gamma is yeah, so this is the net. Yeah, I wrote it here in terms of heat flux and temperature. You could potentially write it in a more general form, just some flux of entropy, external supply of entropy. Yeah, doesn't have to be related to flux. You could do that too.
So what is the phi here, sorry?
Phi is the flux of entropy across a imaginary surface within the material.
So that's not the first, that's not the divergence of the flux that you have.
No, this is correct. This occurs if there is a macro scale flow, but even if there is no macro scale flow, we can have across an imaginary surface, you can have exchange of entropy.
Exchange?
That is this one, correct, yeah. That means, so now you have to be really conceptualized. The same way across a surface, without any movement, you can have momentum exchange. That is the internal forces or hitting of each other, the pressure, or energy. I can have entropy exchange. Now, if I say entropy is related to the heat flux, then the heat flux will give me entropy flux. So entropy of one part of system can go up, the other part can go down. That's because of this flux. In fact, by heating, you do that. So there is an entropy flux, there is an external supply of entropy, because of, say if you have radiation, that should also cause these microstates to be all different. And then there is not equal to 0, and that is the net rate of production of entropy, and that is governed by second law of thermodynamics. This is a empirical, observational, experimental fact that the entropy goes up. And then you can write it in this way. So, I have based on a discrete molecular description of matter, where the only thing that we have are point masses and the position and the intermolecular forces, I derived using this averaging balance laws, mass, momentum, energy, and I also introduced, in a way, just in analogy, not analogy in form of the balance laws. I proposed the momentum entropy balance equation, or entropy imbalance equation. Now, again, you can say, what is the use of it? I knew all of that, and it's true. I hope that when I then derive do the same thing for a much more complex system, that is the multiphase systems, then you can see, okay, now that was helpful. So I could indeed do that, or I think it's enough for today. We stop, not bad time to stop. And so then next time I will talk about, actually, usually what I do is that not go to, again, doing the whole thing now for a more complex system, becomes boring. First, to introduce what I call this rational thermodynamics approach for a single system, for a fluid. So I have the balance laws. How do I develop the constitutive theory to derive Neville Stokes equation, for example, or elasticity, Hooke's law of elasticity, and so forth, okay? So maybe we'll do that tomorrow. All right. Any questions?
I have a question.
Yes.
So at the beginning of the lecture you asked us what about the equations, they are laws or assumptions.
Right.
So you derived some equations, you call them laws.
Right.
Why do you think they are laws? Because you derived them with many, many different approximations and assumptions.
Yes. Now, first of all, I would not agree that I made assumptions. I only made definitions, and I used the laws of mathematics, the formulas of mathematics. I didn't make any assumption except the entropy part.
The entropy.
What assumption did I make? I didn't say, oh, let's assume this or that.
Newton's equation.
This one.
Yeah.
Yeah, but do you give me, I would say it's not an assumption. I would say this is, I don't know what else you could do here.
Well, I mean,
Write it in a different
so
form.
why do you call it Newton equation? Because before Newton, they didn't have that equation.
Yeah, but still, is it an assumption? Or is it that I cannot see, because if the assumption means that there are many possibilities.
I mean, in your approach that you sketched, you used that equation.
That is correct.
Yes, so that is then
In
intrinsically an
assumption.
assumption.
Yeah, okay. In that sense, you can say the existence of particles and their position is also an assumption. That is true. All right, I agree. I made a couple of very fundamental assumptions. But for the rest, I use these starting points, and I didn't make any assumption. That's why I saw law. Another reason, did I say these are solid particles, or gas, or liquid? I didn't say anything. Did I say it's valid only if temperature is between, I don't know, 0 and 100? Or if the velocities are this, or thermodynamic conditions are that? So within the concept of Newtonian mechanics, maybe that's what I should say, these are laws. They are not approximations.
No, I thought it's a simple system, so there are no additional directions, there is one kind of molecules, so many, many different things before you mentioned.
Right, as I said, I will then look at a case where I have 3 different molecules, they are interacting, and then you will see the equations will become a little different, and I'll get something else. But even there, I will not make assumptions. I'll just set the scene in terms of, okay, what are the starting points? You will see that you will start assumptions when we talk about the behavior of the material, because then we have to make assumptions. What kind of material is it? How does it behave? If I, for example, put pressure on it, how does it behave? A solid, a gas, and a liquid, they all behave differently. Then we have to make the assumptions. And then you need what I call constitutive assumptions. But at this stage, what is the law? There are no, I do not know of situations that these are not valid, except Einstein theory. But the balance of mass, I don't know any situation is not valid. What else?
No,
non-local, but even that I can integrate them.
Yeah, general relativity, you
Yeah.
no longer need a mass.
Of course, yeah. No, as I said, if I don't know any situation that they are not valid. That's why I call them law.
Yeah, we also. So if you obtain the Navier-Stokes equations in this way, it will be law or what?
It's not possible to obtain Navier-Stokes equation this way.
Okay.
You will absolutely have to, like in a statistics mechanics, you have to have many assumptions to arrive at Navier-Stokes equation. And we'll do that then tomorrow, then you'll see I have to make assumptions. Okay, any other question? All right, thank you then. See you tomorrow.
Yeah, thank you.